I must have just moved it. Okay, good. I'm glad you please found it. Okay, let's get started with our chapter 5 presentation and notes. So take out your notes that you took yesterday as you read chapter 5. And thank you to all of you who got your total registration stuff done. I appreciate it. So now I don't have to hassle you. The next thing I'll be hassling you about, besides registering, is paying for it if you are not doing the fee waiver. All right, so let's talk about Newton's laws, but now we're going to be looking at them with some applications, including some applications with circular motion. First thing we have to talk about is friction. And there's a lot more to understand about friction than what you learned about last year in Regents Physics. So let's first start by talking about 3 different kinds of friction. 3, not 2, 3. The first is called static friction. Your textbook refers to it as FS. You can write it FFS like we did last year. Static friction is the type of friction that exists before surfaces start to slip. So surfaces are in contact and they are not moving relative to each other. Does that mean things are not moving? No. It just means things that are in contact are moving together. They are not slipping against each other. They are not sliding yet. Now, what you learned last year in Regents Physics still applies. The amount of static friction force is a variable amount. The only amount of static friction you can calculate is the maximum amount, which is at the moment when the object would then just begin to slide, that threshold of motion. So the minimum amount is always 0 if the objects are not even attempting to slide across each other. So there's no motion, like my 2 hands right now, they're not trying to slide. But if I push down and I try to slide them, now there's static friction between them. They're not slipping, but they're trying to. And then once they slip, there's a certain amount, which is the maximum, which can be calculated by taking the coefficient of static friction and multiplying by the magnitude of the normal force. This is how it's written in your textbook, that the static friction force is less than or equal to mu SFN. When it's equal, that's at your threshold of motion. Kinetic friction, FFK, your textbook writes it as F sub K, is the amount of friction when the 2 surfaces then slip and slide. This often happens, for example, in a car when the wheel locks up and the car goes into a skid. That's kinetic friction. The car is now sliding across the road surface. The magnitude of the kinetic friction force is usually fairly constant. We assume it's constant, although there's usually a little bit of variability around a constant amount that can be calculated, and it's usually less than the maximum static friction force, which is why it's easier to keep something moving once you set it into motion than it is to get it to start moving. And the way you calculate that is by taking the coefficient of kinetic friction and multiplying by the magnitude of the normal force. The normal force is the degree of pressing between the 2 surfaces. The third type, which is the new one that we did not study in Regents Physics, is called rolling friction, FFR. This is the type of friction that exists when you have a wheel or a tire, for example, that deforms as an object moves across it. This is why very often you get your car moving, take your foot off the gas. It's going to coast, but it will not maintain a constant speed. It slows down. Why does it slow down? Not because of static friction. Static friction is there with the grip between your tire and the road surface. It slows down because of rolling friction. Rolling friction comes from continual deformation where the road surface and the tires start to peel apart. So this opposes actual motion, causing a car to slow down, for example, because of its tires. If you had a rigid wheel, then that would not exist. Okay, so something that's rigid would not have a rolling friction force to cause it to slow down. The way we calculate this is similar to the way we calculate kinetic friction, except we use a coefficient of rolling friction to calculate this amount. Now, in your textbook, There is a chart which you'll be using to help you solve problems with friction. Notice the problems are only going to involve static and kinetic friction. This chart is on page 120. So you may want to make a note of that is where you're going to get your coefficients of friction to solve the problems. Unlike last year when it was on the reference table, this is not on the AP reference table. So if you need a coefficient of friction, it would be given to you in a problem. Page 120 is where you'll find these coefficients of friction. So you may even want to turn to that now. You'll see it's at the top of the page on page 120. What you might want to do with your textbook that you have at home, or if you're bringing it back and forth to school to solve problems, get some Post-its and put a little tape flag on that page. That way, when you need it, you can quickly turn to that page. There's quite a few charts within the text that we will be using to look up values as we solve problems. But that chart on page 120 at the top, that's what's here. You'll see the different materials. Obviously, they're a little different than what we had last year in Regents. All right, just to quickly review where friction comes from, it's a type of electromagnetic force which comes from the attraction and repulsion of two surfaces in contact at the molecular level. So if I start to deal with a surface like this, what we see here I've got a small surface area. Here I have a large one. The amount of the surface area really doesn't matter in terms of calculating the friction force. It has to do with the amount of pressing between the two surfaces. So a lot of times students think, oh, this one's going to have less friction than this one, even though it's the same object. They have the same normal force being exerted. It's the same two surfaces in contact. This has less friction. No, it doesn't. It has the same amount of friction that this one does. The surface area has nothing to do with it. It's just that there's, as you can see, bigger gaps in between, but spread out over longer areas. So if you dealt with an ordinary surface like your desktop, you already know this. There's friction with your desktop, even though it feels smooth, because as soon as you put it at the microscopic level, like what we see here under an electron microscope, those surfaces have those jagged edges on the top surface. So that's a cross section of polished steel, polished steel is super smooth, like your car hood. Feels smooth, but there's still friction with that. This is a graph that I know you've seen from Regents Physics, where we're showing you how the friction force varies as we apply a force to an object. So here we're seeing the applied force increasing. And notice that the frictional force will increase up to a point. And that point there is when the object then slips across the surface. This is our threshold of motion. And that amount of friction right there is the maximum static friction force, which you would calculate with the equation FFS is mu FFN. Then it levels out, becoming kinetic friction here. So in this case here, when we're on this diagonal line, usually we're dealing with no motion or constant velocity, where two objects are moving together at a constant velocity. Balanced forces, in other words. Here doesn't necessarily mean we're dealing with balanced forces. In your textbook on page 121, so the very next page, you'll see at the top of page 121, there's a yellow box, which gives you a 3-step problem-solving method to help you solve these problems with frictional forces. And the first thing they always tell you to do is to choose a y-axis that's normal to the contacting surfaces. That's perpendicular to it. That's usually what we call your perpendicular axis. And then choose a parallel axis parallel to the surface in contact. And then draw in all your forces. Then apply Newton's second law that the forces in the perpendicular direction would equal the mass times the perpendicular acceleration. So you can solve for the normal force, because the normal force is always perpendicular to your surface. If it's a kinetic force, friction force, you can solve for it using FFK as mu K times Fn. If it's static, then you have to look at the normal force and the coefficient of static friction to see what the maximum amount is. If it's rolling, then you can solve for your rolling friction force using mu R Fn. And then in the parallel direction, you can use Newton's second law. F net in the parallel direction is equal to the mass times the parallel acceleration to solve for whatever it is they're looking for. But you make a free body diagram with all of that stuff. All right. This is the new part dealing with our curved paths. Some of it is what you learned last year, where we have an object moving in a circular path like a car on a flat horizontal road. But then we're going to deal with some banked turns, similar to what you dealt with in the lab that you did for me and wrote the report while I was out. So centripetal force, remember, is a net force component, which is in the radial or centripetal direction. This is the component of the net force which points inward towards the center of the circle. It's not a new force like gravity or a normal force or a friction force. It is just another way to talk about the component of a net force that points inward. And we never draw them on free body diagrams. We never, ever, 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 ever draw a net force or any of its components on a free body diagram. You only draw the actual physical forces that exist. Things like tension force, spring force, normal force, friction force, gravity. Any of those forces can be drawn on a free body diagram. But are you ever going to draw an F net or an FC on a free body diagram? No, and if you do, I'm going to come over and smack you. Not really. Okay, I would theoretically smack you to say, hey, wake up, smell the coffee. We don't draw F nets or FCs on free body diagrams. We only draw the actual physical forces in the direction that they are being exerted. We don't even draw the components initially. Your free body diagrams are just the actual force pointing in the direction it exists. You can then redraw it later with the components of forces, but not in your first free body diagram. If you draw the components with the actual force, you've actually doubled the magnitude of force on your diagram, and that's marked wrong. So make sure that you always look for, if something is moving in a circle, look for some amount of unbalanced force that is pointing towards the center of curvature for the path. That would be your centripetal force or the net force in the centripetal direction. Again, make sure you do not draw FC or F net on a free body diagram. Ever. 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 I can't make that any clearer. All right, let's talk about a car rounding a turn. If you have a horizontal road surface, both the centripetal force and the forward force are being provided by a static friction force between the road and the tires. The static friction force is allowing your tire to grip the road surface, which allows you to have control of your car moving forward or turning. If you're going or moving at a constant speed, the forward component of the static friction force is being balanced by any rearward directed forces of air drag and rolling friction. Air drag, remember, is only significant, and you probably read this in your notes in the chapter. Air drag is only significant once you start to deal with very large speeds or very large surface areas. So for a car moving slowly, that's not really what you're going to consider. Air drag isn't the main thing slowing it down. It's rolling friction that is. If we have a banked turn, a road surface which is no longer horizontal, it's tilted. And we have a lot of these around here in the Northeast because it helps eliminate dependence on friction to allow something to navigate a circular path. Things like an 18-wheel tractor trailer. They have a very high risk of rolling over and tipping, as we've seen in the last week. There were several accidents on the Northway and alternate Route 7 heading over to Troy where those roads merged. While I was out last week, I saw on the news that this, what did they call it? A trailer had 20 cows in it, tipped over. 2 of the cows on that tractor trailer died because of the accident that happened. That road surface was not banked. It was flat, horizontal. If they had banked it, there was less of a chance that the truck would have tipped over because of its center of gravity being high. So why do we bank road surfaces? When we do this, there's a component of the normal force directed inward towards the center of curvature that contributes to a centripetal force, a net force pointing inward. If we do this correctly as engineers, let's say you're going to be a civil engineer, you're designing a roadway system. If you choose the banking angle of your road surface properly, you don't need any frictional force for an object to navigate the turn. That's a wonderful thing, especially here in the Northeast when we end up with a lot of snow and ice on our road surfaces that make road surfaces slippery. We don't have to put as much salt or sand on the road, and a car can still navigate that turn without tipping over. So here's what I mean. Where is the center of curvature for this diagram? It's over here. This is the center of curvature, a vertical axis right here. Notice that the normal force has a component horizontal and a component vertical. That horizontal component by itself, without any friction between this car and the road surface, would be enough to provide a centripetal force to navigate the turn. So what I need you to do, last year in Regents, anytime we showed you an inclined surface, you automatically thought F parallel, F perpendicular for the components of weight. That is no longer going to be true. You have to look at how an object is moving. In this case, you got a road surface like this. Like if you watch NASCAR or anything like that, you know that the cars go up on the road surfaces on the sides. Yes, you know what I'm talking about? And then they keep going around a turn up on the sidewall a little bit. Okay, where's the center? It's pointing inward horizontally. So what we want to do is have one axis perpendicular to that centripetal direction and another parallel to the centripetal direction. So this one, you would not resolve the weight into parallel and perpendicular components. I know you see an inclined surface, but that's not what you do. You have to look at the direction of the acceleration. It's accelerating inward, which means we need one axis up and down and another one horizontal. So what are you going to resolve in this case? The normal force. The normal force gets resolved into parallel and perpendicular components, not the weight. And the parallel component, the horizontal one, is the centripetal force in that picture. You follow what I'm saying? So it's not an automatic thing. You got to think a little bit more in terms of what are you supposed to do. Okay, let's now talk about a drag force. And this is probably the hardest part of our entire course, drag forces, because we need some calculus to do this. I'm not going to ask you to solve all the calculus problems. I'm just going to ask you to set them up because we don't know how to do necessarily U subs with integration and so forth yet. But come second semester, that's all now fair game. So let's talk about what we do with a drag force. First of all, what do we mean by a drag force? A drag force exists whenever an object moves through a fluid. Now, I'm not saying a liquid. I'm saying a fluid. What do we mean by a fluid? A fluid is anything that can flow. That includes liquids and gases. Gases can flow. Air flows from areas of high pressure to low pressure. That's what creates our jet stream, for example. All right, so we're talking about any liquids or gases. Viscosity has a big thing to do with drag force. The more viscous a fluid is, the more drag force it would exert. Do you know what I mean by viscosity? It's like thickness. And it comes from collisions between the molecules in that fluid and the surface area of the object trying to move through the fluid. So drag forces depend on three things: the shape, the properties of the fluid, meaning its viscosity, and the speed of the object moving through the fluid. To demonstrate that, all I have to do, I'll do a couple of things here, a couple experiments with you. Here's a piece of paper. I'm going to let it fall. You can easily see that swaying back and forth. What's that? What's causing that? Air drag or air resistance, opposing its motion. That's coming from this piece of paper's surface colliding with the air molecules that you can't see. If I want to affect how much drag is exerted on it, all I have to do is change the shape of this. There's much less surface area now in contact with the air. A lot less air resistance acting on it. You follow what I'm saying? Did I change the properties of this? No, nothing other than the shape of it. I didn't change the properties of the air, the fluid it was moving through, and I didn't change its speed. To talk about speed, here's what I want you to think about. How many of you drive? Okay. If you don't drive, that's okay. Be the passenger in the car. I want you to open up the window of your car when you're driving later. Stick your arm out. One hand on the steering wheel, the other one out the window if you're the driver. Okay. Just take your foot off the gas. Your car is going to automatically start to move once you're in drive. Most of your cars now have an automatic. That's how when I learned to drive, the first thing my parents did was they took me to Sand Creek Road, Sand Creek Middle School on a Saturday. Nobody was there. And I remember being in that parking lot, turned on the car. That was lesson one. Okay, turn it on, turn it off. I was like, come on. Okay. My father said, all right, turn it back on, put the car in drive, but no foot on the gas or the brake. The car started to move. Your cars will too. As soon as you put it in gear, it will start to move. Not very fast, like 2 miles an hour. That's all you need. Let it go 2 miles an hour with your hand out the window. You're going to feel some air against your hand. Not much. Then put your foot on the gas and go 10 miles an hour. What are you going to notice? More air pushing against your hand. That's more air resistance, more drag. So the speed is related to how much air resistance force you will experience as you move through a fluid. So at low speeds, what we generally observe, this is a general trend. At low speeds, the amount of drag is just proportional to the speed, V. Once you get up to a very high speed, and high is relative, I can't give you, oh, it's 100 miles an hour or it's 1,000 miles an hour. Then it becomes proportional to the square of the speed, V squared. So this is the way we generally write a drag force equation, B, V to the nth power, where that N is either the number 1 or 2. It's a 1 if the drag force is directly related to the speed. It's a 2 if it's related to the speed squared. And that letter B is something which is determined by the fluid that you are moving through. It's a constant of proportionality. So the speed of a falling object, like this paper, will increase until the drag force acting on it balances the weight. Once the drag force balances the weight, because as it falls, it gains speed, it accelerates. That means that this V value goes up, which increases that until you get a drag force that is balancing the weight acting down. And that is what we call your terminal speed. Once you've reached a terminal speed or a terminal velocity, the forces are now balanced. The object will no longer gain speed. It no longer accelerates. And that allows you to solve for the terminal speed by setting the weight of the object equal to the magnitude of the drag force. So if the N is a 1, 1 over 1 is 1, the terminal speed is just the weight divided by that proportionality constant V. If it's a square on the V, the number 2, then you would take the square root of mg over b to determine your terminal speed. Okay. Can you reach a terminal speed if the object is moving upward? Let's think about that for a minute. I'm going to go to my document camera for a minute. Grab another piece of paper since that one's all crumpled up. Terminal speeds, I think we understand, they can be reached fairly easily if the object is moving downward. Because if I'm moving downward, here's the object. I'd have its weight pulling it down. And I'd have this drag force pulling it upward, which is equal to BV to the nth power. Is this in equilibrium right now, the way I drew that? No. which means this would be accelerating downward. This is falling downward. How do I know it's going down? Because the drag force opposes motion. It's like friction. So in this case, there would be a net force in the vertical direction equal to Fg minus F drag. In other words, mg minus bv to the nth power, and that would equal ma. Okay, do y'all follow me on that? Once this object is now moving downward, but it's reached that terminal speed vt, then we know that Fg, which is still mg, has to balance this drag force. These are now balancing each other out, which means that the acceleration is now 0. This happens at that particular speed only. So in this case, there is no net force, and the magnitude of the weight is equal to the magnitude of the drag force. So mg would equal bvt to the nth power. That is the specific terminal speed, which means that your terminal speed would be found by doing mg over b to the 1 over n power, depending on whether this was a 1 or a 2. Remember, n is either 1 or 2. There's no other option. Now, let's say that question I asked a moment ago, let's say the object is moving upward. Can you name the forces that would be acting on it as it goes up? Yep, which way? Yep. Is that the only thing acting on it? Ruben, I see you said no. What else is acting? I'm sorry? Yeah, which way? Also down. That's it. Can you reach a terminal speed in this case? No, because can this ever be in equilibrium? As it's moving upward, no way. Both of these together would produce an acceleration in the downward direction, which would be found by doing Fg plus the drag force. Notice that the largest possible acceleration would occur in this situation. Well, let's talk about it when it reaches the top of its trajectory. At the top of its trajectory, because both of these are going to cause it to slow down. And as it slows down on the way up, this speed gets smaller, which means we get less and less and less drag. So once we reach the top where it stops moving, now the only force acting is the weight. And at that moment in time, the only acceleration is the acceleration of gravity, which is pulling it down. And once it's past that, what does it do? It goes to this scenario. When you throw something up, it stops and then it comes down. So this would have non-uniform acceleration, which means that we can only find the acceleration using calculus with these equations. Okay. Any questions on that? Does that make sense? You got to start with your free body diagrams to help you understand all of that. This is the situation for this person who jumped out of a plane and they're falling. So we can see that the drag force is directed upward. There is their weight acting downward. When those two arrows are the same length, then we've reached our terminal speed. All right, any questions on the presentation? No? All right, then what I'd like you to do now is pull out your textbook and your reading guide, So that way you can start working on homework assignment 22 if you have not already, which is due tomorrow. 22 is the reading guide. If you've already completed the reading guide, chapter 5, which is due tomorrow, then you should start working on assignment 23, which will be due on Thursday. Okay? Questions for me? All right, so I'll let you guys go ahead and get to work on that.